So we start. This is mathematical analysis for recursive as well as non-recursive algorithms. We try to visualize the concepts. So this is especially once again for you, my dear students and young researchers, and you can reach me at dr.christoananth@gmail.com. So before beginning the session, let me thank God for giving me this opportunity to deliver this useful session, to share my knowledge among my fellow national, international participants, students, and young researchers. So in this class, we discuss about the analysis of non-recursive algorithms, about the analysis procedure, how you try to specify the binary length. Then you try to analyze the second part, which is recursive algorithms. We understand the procedure to the recursive algorithm about its binary representation. Then we try to examine an example, Fibonacci number sequence. Then how you try to apply to the Fibonacci recursion, how you try to apply the recursive algorithm for Fibonacci numbers. Then of course, we'll be giving you the independent work for you. Please complete them at your best available time. And at regular intervals, I'll be giving you some short videos to discuss the knowledge in our topics. So this is an analysis of this non-recursive algorithm. So normally, whatever the basic operations that we will be analyzing, we will be applying them, and here you tend to apply the for loop accordingly. Okay. So for this, we will be having some series formulas. There will be an algorithm to find the maximum element. Okay. So here is the algorithm, max element af 0 to n minus 1. The maximum value you are assigning it to the starting part, which is af0, for I equal to 1 to n minus 1, and then do if a of I is greater than maximum value. Now you assign a of I to that maximum value, and you try to return the maximum value. So maybe if you can analyze some questions regarding this one. What is the problem size? Like what is the most frequently used operation? You can ask for yourself whenever you are evaluating any algorithm, and whether it follows the best case or maybe average case or maybe worst case accordingly. And what are the different types of comparisons that you can evaluate, that you can find it to be C of n, and you can compute a formula for the comparisons. So it is summation I equal to 1 to n minus 1 over 1. Okay, so that n minus 1 you can take it outside. The n minus 1, this summation limit you can give it as summation of phi of n. Okay, so here you have to decide on the problem size specification. You have to identify the basic operation accordingly, and for each of the case you have to analyze the average case, best case, and then worst case. Then you have to find the number of comparisons. For this, you have to go with the count, you have to set up the sum, and you have to evaluate the order of the sum accordingly. So we have some series formulae, like multiplication of series. Let us take in the case summation I equal to 1. It is u multiplied by c ai. So since c it's a constant, you can keep it outside. So c multiplied by summation I equal to 1 u into a of I. For example, if you have to add two sequences, then summation I equal to 1 u of ai plus bi. So that you can take separately as individual addition. Summation I equal to 1 u ai plus summation I equal to 1 u bi. Then you will go with the constant sequences addition also. So summation I equal to 1 u1 equal to u minus l plus 1. Then you will have the sum of linear sequences. Summation I equal to 0 to n I equal to n into n plus 1 by 2. So this is nothing but the summation value. Okay, so it is actually the length of the sequence times the average of first and last elements. Then you can check for uniqueness also. So maybe from 0 to n minus 2, you are going to check the remainder with equality, and for this you will have an algorithm. Unique elements a of 0 to n minus 1 for I equal to 0 to n minus 2. Then you go with the do for loop. J, again you initialize I plus 1 to n minus 1. Do if a of I is equal to a of j, then you return false. Else case you return true. So here also you specify problem size, basic operation. The worst case and best case for this is different. Best case is when the first of the two elements are equal, then you have to specify, find the value of theta n. Worst case is nothing but if the array elements are all unique, then you are going to have the sequences for the for loop which are executed. Then you will find the sum. C worst of n is equal to summation I equal to 0 to n minus 2, summation j equal to I plus 1, it is n minus 1. Then you solve for the both the worst cases. For example, C worst of n is equal to summation I equal to 0 to n minus 2, n minus 1 minus of I plus 1 plus 1. So you will have summation I equal to 0 to n minus 2, it is n minus 1 minus I, which is equal to summation k equal to n minus 1 over k. For this case, k equal to n minus I minus 1. Then for the worst case again, summation k equal to 1, n minus 1 k equal to n minus 1 into n minus 1 plus 1 by 2. So it's actually that can be simplified as n into n minus 1 by 2 epsilon, okay, phi of n square. Okay, so you will be having like n into n minus 1 by 2 comparisons, and definitely we should pre-sort also. So we'll have the binary length computation algorithm, binary of n, count equal to 1. So with this case, when n is greater than 1, then you will have count plus plus, you try to increment the count, and you will have n equal to floor of n by 2, okay, and you return the count. So here also you will specify the problem size. Basic operation is nothing but the comparison in the while loop, and here unlike the previous case, like worst case and best case are different, but here worst and best case are the same, okay, because we are having n greater than 1 and count plus plus. So that is the reason we are assigning n equal to floor n by 2. So worst case and best case are the same, and you will have some, you will have how many times the while loop is being executed. So maybe exactly lg of n plus 1, okay, otherwise it will fail, okay. So c of n is equal to summation I equal to 1 lg of n plus 1, and you solve for the c of n value lg of n plus 1 minus 1 plus the function which is nothing but epsilon theta of lg of n. Next, you try to analyze the recursive algorithm. You try to find the factorial. Like maybe 6 factorial means 6 multiplied by 5, multiplied by 4, multiplied by 3, multiplied by 2, multiplied by 1. So this is how it goes. And you know very well, according to the initial conditions, 0 factorial is equal to 1. So actually the recursive definition is nothing but n factorial is equal to n multiplied by n minus 1 factorial. Okay. So this is how it goes. Maybe like n minus 1 factorial means n minus 1 into n minus 2 the whole factorial. Okay. So maybe we will have the algorithm f of n. So if n equal to 0, then you try to return 1, that is the best case. And for the recursive call, you will have f of n minus 1 multiplied by n. Okay. So similarly for the multiplication also you have the same thing. M of n is equal to m of n minus 1 plus 1. So that is actually a recursive formula. So we have an initial case also, we will have the initial conditions m of 0 equal to 0, that is nothing but the initial condition. Then you solve by the backward substitution. Maybe let us take in the case m of n. You will have m of n minus 1 plus 1. So maybe you can repeat the order like m of n minus 2 plus 1 whole plus 1. So maybe you will have m of n minus 2 plus 2. For example, this 1 and 1 gets added, you get plus 2. Okay. Similarly, m of n minus 3, you try to repeat the order plus 1 plus 2. So this becomes 3. Okay. So this is actually substituted for m of n minus 2. In place of m of n minus 1, we are going to have m of n minus 2. And instead of m of n minus 1, we will have m of n minus 3. So if you can evolve the pattern, go on and on, it will become like minus 3 and plus 3, it will become 0, and then m of 0 plus n. So this is how it comes. So that is actually m of 0 plus n. So the maximum is actually n. So you can consider it as n. Okay. So in this case, m of n is equal to n, and therefore m of n multiplied by epsilon theta or maybe phi of n. So this is the procedure for recursive algorithm. Here you specify the problem size, identify the basic operation, perform the worst case and then average case, and you try to write a recursive relation. keeping into mind the initial conditions, and you try to solve the recursive relation and the order of code. So maybe in the initial call you'll have work, recursion, and then best case, and after recursion it goes to the initial call once again. The process is completed, and when you try to return the best case, then you output the result. So this is the binary representation. We have algorithm like the bin recursive function of n. If n equal to 1, then return 1. Else case, you return the bin recursive floor of n by 2 plus 1. You specify the problem size. Basic operation is nothing but addition in the recursive call. Here, once again, there is no much difference between the worst case and then best case. And you have the recursive relation a of n equal to a of floor of n by 2 plus 1. Here the initial condition a of 1 equal to 0, and you try to solve this recursive relation. So maybe we can have a variable substitution also, n equal to 2 power k. So accordingly this is correct. So in order to still get the exact result, you can go for the smoothness rule. So it is actually, we are specifying a function t of n which is non-decreasing, and f of n is smooth. Okay. So maybe let us take in the case if t of n and theta of phi of n for n pass of d, then maybe t of n multiplied by epsilon of, or maybe summation of theta of phi of n for all values of n. Okay. You substitute n equal to 2 power k in these functions. So a of 2 power k equal to a of 2 power k minus 1 plus 1. For the initial condition, a of 2 power 0 equal to 0. Okay. Here a of 2 power k is equal to, once again you iterate, a of 2 power k minus 2 plus 1 plus 1. So here instead of a of 2 power k minus 1, here you have a of 2 power k minus 2 plus 2. Similarly, if you try to iterate, you have a of 2 power k minus 3 plus 3. So simply we can say, instead of the minus 3, you will see like a of 2 power k minus I plus I. Let us take in the case this I equal to k. So maybe a of 2 power k minus k. This is actually 2 power 0. It is actually 1. Okay. A of 1 plus k. So that is actually the total function will be equal to this k. So let us take in the case if you take this as a logarithmic function of n. So a of n is equal to log of n plus multiplied by theta into phi of log of n. Here you have the Fibonacci number sequence, like addition of numbers, like 0, 1, 1, 2, like 0 plus 1 it is 1, 1 plus 1 it is 2, 1 plus 2 it is 3, 2 plus 3 equal to 5, and so on. Okay. So we will specify a condition. Okay. So f of n is equal to f of n minus 1 plus f of n minus 2. So the previous things you add, and the summation will be giving you the new result. This is for the case for n is greater than 1. For the initial conditions, maybe like f of 0, f of 0 is equal to 0, this is 0, okay, and f of 1 is equal to this one, okay, and we specify a homogeneous second order linear recurrence with constant coefficients. So a x of n plus b x of n minus 1 plus c x of n minus 2 equal to 0. So for this case, all the recurrence becomes 0, and it will be a homogeneous condition. So you try to apply this to the Fibonacci recursion. Okay. So x of n is equal to r power n. So we specify a order. So a r power n plus b r power n minus 1 plus c r power n minus 2 equal to 0. What you do? You divide by the recursive function r power n. So maybe a plus b power r plus c r square equal to 0. Okay. So once again, it's a quadratic equation of second order. So you'll have the roots to be x of n is equal to a r1 power n plus b beta r2 power n. So you know that f of n minus f of n minus 1 minus f of n minus 2 equal to 0. So you will have the characteristic equation nothing but r square minus r minus 1 equal to 0. You specify the roots. Okay. So this is the general form of the solution for the Fibonacci recursion. So you will have f of n is equal to alpha phi power n plus beta phi dash power n. Okay. So the initial conditions alpha plus beta equal to 0 and phi alpha plus phi dash beta equal to 1. You specify, substitute the value of alpha beta, and you will get the function. Okay, 1 by root 5 phi n minus phi dash of n, which is nothing but if you take phi n outside, phi n divided by root 5. So you have the algorithm f of n. So in this case, for n less than or equal to 1, you return n. Else case, you return the f of n minus 1 plus f of n minus 2. So this is the thing. Problem size is n, and basic operation in the is the sum in the recursive call. No difference between the worst and average case, and of course recursive relation is nothing but a of n is equal to a of n minus 1 plus a of n minus 2 plus 1. So the initial conditions a of 0 equal to a of 1 equal to 0, or a of n minus a of n minus 1 minus a of n minus 2 is equal to 1. This is the inhomogeneous recurrences because of this one value. Okay, and for the inhomogeneous problem, we are going to compute the sum of the solution to the homogeneous problem, plus you are going to add the solution only for the inhomogeneous part. Okay, so in this case, a of n is equal to b of n plus initial condition of n. So here a of n, it is nothing but the solution for the inhomogeneous problem. B of n is the solution to the homogeneous problem, and I of n, it is nothing but the inhomogeneous part of the problem. Okay. So for this, like I of n equal to 1, you substitute a of n is equal to b of n minus 1 into the recursion, and maybe you will specify b of n minus b of n minus 1, b of n minus 2 is equal to 0, provided the initial conditions b of 0, b of 1 equal to 1. So the same relation we are going to have, but we can have a conclusion or an overall solution to the problem. A of n is equal to b of n minus 1, which is nothing but function of n plus 1 minus epsilon phi of, theta of phi of n, that is the exponential function. And we'll have an iterative algorithm that will be a common one, keeping into consideration homogeneous as well as inhomogeneous part. So it is Fibonacci of n, f of 1, that's nothing but 0, f of 1 is 1, for I equal to 2 to n, then go over the loop f of I equal to f of I minus 1 plus f of I minus 2, then you return the function of n. So you can specify this order is nothing but O of n.